Okay, here is another function that we can look at. Y, it's a rational function, so y is equal to x plus 1 squared over 1 plus x squared. If I square the top, it would look like x squared plus 2x plus 1. And this function can also look like x squared plus 2x plus 1 divided by, I just rearranged 1 plus x squared, so x squared plus 1. If we use long division, x squared plus 2x plus 1 divided by x squared plus 1, that's just dividing x squared by x squared, and that's 1. 1 times x squared plus 1, okay, we have x squared plus 1, then taking the difference of this minus x squared plus 1, we have 2x, so 2x is the remainder. So another way of writing y is equal to, another way of writing this function is y is equal to 1 plus 2x over x squared plus 1. What is the first derivative? Of course, the first derivative of 1 is 0. Then the first derivative of this ratio, the derivative of the top is 2 multiplied by the bottom minus the derivative of the bottom, which is 2x, times the derivative times the top, 2x. And if we distribute 2 here, and then this becomes minus 4x squared, we see that the numerator becomes simplified into 2 minus 2x squared over the square of the denominator. Now you set that equal to 0, and you will get the critical values on the top, and the denominator will never be 0 because x squared plus 1 is always positive. Okay, now suppose we didn't do all these long division, right? Suppose we didn't do all this long division. You can go ahead and find the first derivative right from the beginning, right here, using the quotient rule. So we square at the bottom and then take the derivative of the top, which is 2 times x plus 1. Then the derivative of x plus 1 is 1 multiplied by the bottom minus, okay, whatever is on the top, multiplied by the derivative of the denominator, which is, the derivative of the denominator is 2x. Okay, and then do all the manipulation or algebra here. We see that x plus 1 is a common factor on the numerator. You see that? X plus 1 is a common factor, so pull it out. 2 is also a common factor, so pull that out. What is left would be, from here, we pull out x plus 1, so it's what is left is 1 plus x squared minus one of the factors of x plus 1 is also left, and x. And simplify all of this, we will get 1 minus x. Set the numerator to 0, and we see that x plus 1 is 0 or 1 minus x is 0. So the two critical values are 1 and negative 1, which you will get the same answer when you set this numerator here to 0. This is, when we factor this out, it's going to look like this. See, you'll get the same answer for critical values. Alright. First derivative test, we could use the first derivative test to find the, whether it's increasing or decreasing at negative 1, to the left of negative 1 and to the right of negative 1, and so on and so forth. Suppose we test negative 2. So y prime at negative 2, this would be negative times positive over, okay, negative times positive over positive will give us negative. Okay. What about between negative 1 and 1? Let's use 0. So if x is 0 here, then we have positive times positive over positive. This means in this interval we have positive. So there is a decreasing and an increasing occurring at x equal to negative 1, to the left of negative 1 and to the right of negative 1, which means there is a local minimum occurring at x equal to -1. What about to the right of 1? Let's test 2. So y prime at 2 would be, this would be positive times negative. So positive times negative over positive would give us negative. So you see that there is a change of sign. So that means again, to the left of 1 it's increasing, and to the right of 1 is decreasing. So we have a local max occurring at x equal to 1. We have a local min occurring at x equal to -1. Alright. So far what we have found is that we took the first derivative of this function, and then we found local extreme values, local max and local min. What about points of inflection? Which means we have to take the second derivative of y. Okay, so far that's what we've got. We plug in -1 here, and if this is -1, then y is 0. If x is equal to 1, then y is equal to 2. Because that's just 4 over 2, which means y is equal to 2. So we find points of inflection by taking the second derivative. So far this is our first derivative. Taking the second derivative would be differentiating y prime again. Here's how it looks like. Square the denominator, okay? And then on the top, take the derivative of 2 minus 2x squared. Okay, so that's minus 4x. And then multiply by the denominator. Minus, take the derivative of the bottom, which means you bring down 2 times 1 plus x squared. Using chain rule, multiply the derivative of the inside. So the derivative of 1 plus x squared is equal to 2x multiplied by the numerator. And when we do that, we pull out negative 4x because there's 2 and 2 there, so that's -4. And then x is a common factor right there. So we pull out minus 4x. Also, 1 plus x squared, the quantity 1 plus x squared is a common factor, so pull that out as well. So what is left now would be one of the factors of 1 plus x squared plus, because we pulled out a negative, okay, so now it's plus, what's left is just 2 minus 2x squared. Okay, simplify the numerator, and this is what we get. Right, now, this is the second derivative. We set it equal to 0. Okay, now the denominator will not be 0, but the top, we can set that equal to 0. We see that minus 4x is 0, or 3 minus x squared is equal to 0. So if we set this 3 minus x squared to 0, that means x squared is equal to 3. Take the square root of both sides, we get that x is equal to plus or minus the square root of 3. And of course here, x is just equal to 0. So the two critical values for points of inflection would be 0 or plus or minus the square root of 3. Okay, let us now check for concavity by looking at the change of sign of the second derivative. Okay, so we've got here, we test 0, we mark our number line, that's the square root of negative square root of 3, 0, and square root of 3. Okay, negative square root of 3 is approximately 1.7, so we can test negative 2, we can test negative 1, and then from 0 to 3 we can use 1, and then 2 here. Now we check y double prime, okay, at negative 2. So this becomes negative. Negative 4 times negative 2 is positive. So that is, we have positive, okay, times 3 minus negative 2 squared, that's 3 minus 4, that would be negative, divided by positive, That's negative. Okay? Now from negative 3 to 0, we test negative 1. So y double prime at negative 1 would be, okay, the first would be positive, and then 3 minus negative 1 squared would be positive, divided by positive will make it positive. Okay, so we see that there is a change of sign of the second derivative from negative to positive, so negative 3 square root of 3 is a point of inflection. Let's see if 0 is also a point of inflection. Okay, so y double prime at 1 would be negative times positive over positive would make it negative. Okay, so we have negative, positive, negative. Again, from positive to negative means that 0 is a point of inflection. What about to the right of square root of 3? If we try 2, what is the second derivative when we plug in equal? What is the sign of the second derivative when we plug in x equal to 2? We have there 4 times 2 would be negative 8. So that's negative times 3 minus 4 is negative over positive would make it positive. So we have those change of sign, negative, positive, negative, positive. Alright? Which means all of these critical values are points of inflection. Whenever you have a change of concavity from concave down to concave up, concave down to concave up. So we have those points of inflection occurring at x equal to negative square root of 3, at 0, and at 3. Okay. Let's look at the different points of inflection. And it's at when x is equal to negative square root of 3, when x is 0, and when x is equal to square root of 3. And again, here it's concave down to the left of square root of 3. Then it's concave up from square root of 3 to 0. And then from 0 to square root of 3, it's concave down. And then to the right of square root of 3, it's concave up. And also we found that our critical points for local max and min occurs at when x equal to negative 1, y is equal to 0. When x is equal to 1, y is equal to 2. See that there's a local maximum occurring there because it's concave down. There's a local minimum occurring here because it's concave at x equal to negative 1. And we know that y equal to this rational function would have a horizontal asymptote because the limit as x approaches plus infinity or negative infinity is 1. So you see that the highest power here is x squared and the highest power at the bottom is also x squared. So that's why the horizontal asymptote is 1. Remember, when we want to find the horizontal asymptote, we look at the top and the bottom. If they're equal, it's just the ratio of their coefficients, and both coefficients are 1. So the horizontal asymptote is y equal to 1.